Hawking radiation was theorized in 1974 by Stephen Hawking, one of the great scientific geniuses of our time. Stephen Hawking was born in 1942 in Glasgow, Scotland. He got his undergraduate degree in physics and later his master's in mathematics at Cambridge. When he was 21, Hawking was diagnosed with ALS, yet he was able to make some of the biggest scientific discoveries in his field. Everybody knows the name Stephen Hawking, the scientist and the man in the wheelchair, but let's see how much people actually know.
So I know that Stephen Hawking was a professor at Cambridge and he specialized in astrophysics.
He's a scientist, right? I think.
Right. He's a famous British scientist who has contributed to the field of physics and astrology.
I know he had something to do with black holes.
He was on the Big Bang Theory.
I don't know much about his scientific inventions, but I do know about his book, A Brief History of Time, which I don't quite understand about it.
First, let's give a little introduction into Stephen Hawking's work. Einstein gave the world the theory of relativity, which explained the motion of celestial objects to a high degree. He also predicted the existence of black holes. Around the same time, Niels Bohr came up with his atomic model, which showed us the internal structure of an atom. This led us to the quantum theory. Both scientists tried to combine the theory of the big and the theory of the small, but they were not successful. Stephen Hawking was the only one to combine these two domains, giving us Hawking radiation. Before we can explain Hawking radiation, we need to understand what a vacuum is. Is a vacuum really empty? No, it's not. According to the Oxford University Press Journal published in 2009, every instant a new pair of opposite particles is created, and the next instant they annihilate each other, giving us the apparent picture of empty space. Thus, the box is not really empty but filled with particles. These particles are called virtual photons. Here's an experiment which proved that this is true. When two mirrors are placed nanometers apart in a vacuum, the Casimir effect predicts that these mirrors experience an attractive force. Let's see why. By the theory of Casimir effect, particles are randomly created and annihilated every instant. Since there is less space between the mirrors than outside, the number of particles being created between the mirrors is less than the number created outside, and this creates a pressure difference which ultimately causes the mirrors to move together. To an observer, this looks like the mirrors are experiencing an attractive force out of nowhere. Predicted by the Dutch scientist Hendrik Casimir in 1948, this effect is key to explaining the concept of Hawking radiation. Now let's see how a black hole is created. Anything can be a black hole. You heard that right. Yes, any material can become a black hole if it can be compressed to small volume, at what is called its Schwarzschild radius. Let's take the Earth for example, which has a radius of 4,000 miles and a mass of 6 × 10 to the 24th kilograms. Now, if the Earth were to shrink to 3.5 inches, which is its Schwarzschild radius, then the density of the material would become very high since the mass has not changed but the volume has decreased. This high mass density creates a rupture in space-time and causes a strong gravitational pull and makes Earth a black hole. The good news is that this cannot happen to the Earth, but massive stars about 1,000 times bigger than our Sun can slowly die out and become a black hole. As you might have heard, nothing can escape the enormous pull of a black hole, not even the fastest thing in the universe, light. A ray of light traveling near a black hole bends and falls into it, so technically we cannot see a black hole from Earth since it sucks in all the light. But Hawking predicted something astonishing. He said that some particles escape the pull of a black hole. This escape of particles is known as Hawking radiation. The boundary line around a black hole beyond which nothing can escape is called an event horizon. Now recall the Casimir effect and think what would happen if these particles were formed exactly at the event horizon. According to a paper published by Hawking himself in 1975, one of these particles would be sucked into the black hole since it is beyond the event horizon, while the other particle loses its twin and wanders out. The twin particle which is consumed by the black hole has a negative mass. Thus the black hole's mass reduces every time this occurs, and over an extended period of time this leads to the demise of the black hole. As the black hole gets smaller, the Hawking radiation increases, thus the black hole becomes brighter and eventually it explodes. Now you know about Stephen Hawking's most influential contribution to science. He steered us in the right direction with Hawking radiation, but this topic needs more research by future generations. understanding black holes can potentially give mankind a giant leap towards discoveries such as teleportation and time travel. Hopefully, now you understand why Stephen Hawking was one of the greatest minds of our time.